So which metal is being oxidized and which metal is being reduced? And is this equation balanced?
No.
Okay. Then how do I go about balancing it?
Let me do it.
Where would I start?
I put a 2 in front of the AuNO33.
2 here. Okay.
And then a 3 in front of the MnNO32.
Okay.
And then a 3 in front of the Mn on the reaction side, and then a 2 on the Au on the product side.
Okay. So let's check it out. Au. So we got 2, 2, NO3. We have 6, 6, and Mn. We have 3 and 3. Okay, looks balanced to me. Okay, so tell me who's oxidized and who's reduced. What is the oxidation number for Mn?
Zero.
Okay, good job, 0. And then what about Au over here? Au. What do we know about, what was that?
I don't know how to find the oxidation number for the transition metals. Can you go over that for me?
Sure. What is the second rule to oxidation, to determining oxidation numbers?
Ions are equal to the ion charge, or the oxidation numbers are equal to the ion's charge.
Oh, so oxidation number will be equal to the ion's charge. Tell me, is gold an ion here? Let me help you out. I forgot to put my AQs here. Is gold an ion? Christian, is gold an ion?
Is gold? No, it's not an ion.
Are you sure?
The nitrate is an ion.
So the gold nitrate is an ion. So it's an ion in this complex?
Well, I mean, it does have less electrons because they're sharing. They're not sharing, but it's taking one.
Okay, so it's an ionic compound. Is that what you're telling me?
Yes, it's ionic compound.
Okay, so since it's an ionic compound and it's in an aqueous solution, what happens to that when it becomes an aqueous solution?
It dissociates.
It dissociates. To what?
So the gold would take the 3.
Okay.
That's how you find it, is on its, okay.
Its charge, that's right. So the gold would have a 3+ charge. And we know that the nitrate is going to be what as a whole?
Negative.
Well, -3.
Each nitrate?
Well, not each one, but since there's 3 of them. So you
Okay.
said as a whole, so I just thought you meant all 3.
Okay. I didn't mean all 3 of them. I just meant the one.
Oh, okay.
I meant the whole polyatomic ion, right? Okay, so then if each of the nitrates, let's write this out so we can see what we're talking about. Since each of the nitrates are looking like this, what is the charge on the nitrogen? Or I'm sorry, what is the oxidation number on the nitrogen?
On a what?
On the nitrogen.
Three negative.
On the nitrogen? Are you sure?
Are you talking about nitrogen by itself or nitrogen?
No, I'm talking about nitrogen. What would be, yes, I'm talking about the oxidation number on the nitrogen only. So what would be the oxygen?
In the nitrate, correct?
In the nitrate, yes.
Would it be 6?
2 times -2 times
5.
7, because you have to get it equal to the negative. And
Okay, wait. It has to be equal to the negative, right? So somebody just said that it has to be equal to the negative.
Yeah.
So if it's equal to the negative, so we have a negative. How many oxygens do I have?
You have 3.
I have 3. And oxygen, what is the the oxidation number for oxygen?
-2.
2.
-2. So -2 times 3
6. -6.
is -6. Okay.
So it has to be 5.
So then it has to be 5, right?
Oh yeah, I forgot.
Okay. On the other side of the equation, product side, we have our gold medal. So if we're looking at the total ionic equation for this guy, what would that be? What would this break up into? Come on, Abby.
Wouldn't the MN be 0?
Would it be 0? The oxidation number would be 0 on it.
Wait,
It's
no.
in this complex now.
Oh, yeah.
So well, first, what ions are these guys going to break up into? Are they going to break up into ions? Manganese nitrate. I'm sorry,
Isn't
manganese 2 nitrate.
Gonna break up into ions? Anything with nitrate?
Okay, so it is going to break up into ions. So what is going to be the charge on the manganese?
2.
2. Cassie, come in with the answer.
Sorry.
Good job, Cassie. Okay, and then what would be the other ion?
Nitrate.
And how many would I have?
Six.
Okay, so what would be the oxidation number on the nitrate?
Would it be the same?
Numbers.
Wouldn't
What was it?
Wouldn't it be the same, the 5 and -2?
Okay,
Because it's the same compound, right? Because you'd have
That's
6.
right. And then
It's aqueous. I don't know.
what about the manganese?
Three.
The manganese is going to be 3. What is the second rule for oxidation numbers, Darlene?
Well, doesn't it have to, since MnNO3 doesn't have a charge, doesn't it have to balance it out?
What is the second rule for oxidation numbers?
Hold up.
Monatomic ions numbers equals the ions charge.
The ion's charge. What is the ion charge here?
2.
It's 2. So then the oxidation number is going to be 2, right? What about gold?
0.
That's right, 0. Okay, so we're going from an oxidation state of, or magnesium, of 0 to +2. Is that oxidation or reduction?
Reduction.
Are you sure?
No.
What does reduction mean?
Yeah, that would
You're gaining electrons.
Okay, so if I'm going 0 to +2, am I gaining electrons?
You're losing electrons.
I'm losing electrons. Ah,
First.
so Leo, right? Leo, loss of electrons, which is oxidation. And then with the goal, I'm going from a +3 to a 0. Are you losing electrons or are you gaining electrons?
Gaining.
Okay, so if it's gaining electrons, it's GR.
It's reducing.
Okay, so the green is reducing. Simple?
No, but I'm getting there.
Okay, so let me do this twice, since I have what, maybe 3 people that were really answering questions or 4. You better know this because this will be on the exam. This is not an option. You need to know this. And if you don't know this, you better start talking to the tutors because this is the 3rd time that we talked about this topic. You need to start picking it up. Are we clear?
Yeah.
Yeah.
Okay, good. So with that, and this is an easy one. So when I give you a hard one, which is what I'm going to go over right now, then, and there's a strong possibility that's going to be on the exam too. So you want to be sure that you have a grasp on it. Okay, so to balance redox equations that are kind of complicated, and you guys are going to run into ones that are going to be complicated. The way it works is that your redox reaction is basically being done in aqueous solution. And since it's being done in aqueous solutions, you can actually take advantage of that by utilizing water, hydronium. Hydronium is often, we write it as H+ for simplicity, but it's also H3O+, and the hydroxide ion. And the reason why we have access to this is because since the solution, or since we're in an aqueous solution, we have abundant amount of water. And we know that we can utilize water, and water breaks up into the hydronium ion and the hydroxide ion. Okay, so that's to our benefit. Okay, so these species, water, the hydronium ion, and hydroxide ion, they're not going to change their oxidation state, right? They're kind of just, although they're participating, they're more like spectators, okay? Because their oxidation state isn't going to change on either side of the equation. So, and as I said, often it'll be really hard to balance certain equations just by looking at the equation itself. So this is one way, particularly when we're talking about redox equations. So the best approach is to actually start by breaking the reactions into two halves, an oxidation half and a reduction half. Okay, so let's talk about this. I'll give you the steps, make sure you get them down, and then we'll start with an equation. Okay, so the first thing that you want to do is you want to split them up into an oxidation and a reduction reaction. Then you want to make sure that all of the elements except for the oxygen and the hydrogens are balanced. And then after that, you want to make sure that you've balanced your oxygen atoms with water. So you're going to use water to balance any oxygen atoms that you have. And then you're going to use hydrogen atoms. You're going to balance your hydrogen atoms by using the hydronium ion, H+. Okay. And then the last thing that you're going to do is, well, it's almost the last thing you're going to do. You're going to balance the charge of the electrons. You want to make sure that the charge is balanced. And so, so you want to make sure that, let's say, if you have a total plus charge on your reaction on one side, you want to make sure that you have a total plus charge on the other side of the reaction, on the product side of the reaction. Okay, so you shouldn't be changing your overall charge on the reaction. Are you clear on that?
Wait, can you repeat that again?
So this rule here, so you want to make sure the overall charge on the reaction on the product side, reactant side, equals the overall charge on the product side.
And that's on rule 5.
Yeah, that's what rule 5 is basically saying. And the way you do that is by using electrons, right? So you add electrons as needed. Okay. So then let me add a little bit more. Come on. Okay. If necessary, you want to multiply each coefficient by, each half reaction by a coefficient so that the equations will have equal amount of electrons. So on one, the one that's gaining electrons should equal the one that's losing electrons. The number of electrons that are being gained should equal the numbers of electrons being lost. So those equations, when you add the equations together, they should balance out. I know you're like, I have no idea what the fuck you're talking about. I can't visualize it. Don't worry, we're going to go through an example so you can visualize it here in a second. So then part 7, the seventh step is basically adding the two equations together, and then you're going to remove those that are spectators, the ones that are on both sides of the equation after you add them together.
So this is like your ionic equation, but just using your oxidation numbers.
That's right. Yes. So it's another layer to the ionic equation. Okay. So for reactions that are occurring in basic media, so that basically means that we have excess hydroxide ions, you're going to have to do a couple of extra steps. So then in this case, you're going to add the OH ion to both sides so that you have equal numbers that are equal to the H pluses that you have available. And then on the other side of the equation, you want to contain both your H plus and your OH, your H pluses and your OH minuses. They're going to be combined to form just water molecules. And then you're just going to remove any abundant amount of water molecules that you may have. Okay. And then the final part of it is that you're going to check both sides of the equations for the total number of atoms and then the total charge to make sure it's balanced. Okay, so 9 steps. Okay, so here's our trial run. What was the first step?
Right, half reactions.
Okay, so for writing half reactions, tell me which one is our redox reaction and which one is our oxidation reaction based upon what you see. Iron going to iron 3 plus. Is that oxidation or reduction?
Oxidation.
Reduction.
Okay, so we're going from a 2 plus to a 3 plus. Somebody said oxidation, somebody said reduction. So if I'm going from a +2 to a +3, what must be happening?
You're losing electrons.
I'm losing an electron. Okay, so then it's oxidation, right? Leo. Loss of electrons, oxidation. Okay, so by default, the dichromate ion going to chromate 3 plus must be
Reduction.
reduction. And we can kind of test that out too, because we know that if we have 7 oxygens, each oxygen has a what oxidation number?
-2.
So 7 times -2. So that means chromium must be, we have 2 chromiums. So we'll say 2 Y.
It must be 6.
So it must be 6, huh? Okay. So Y must be 6. So each chromium must be 6. So if we're going 6 to +3, that means we're doing reduction, you said. So GER. Gain of electrons, reduction. Okay. Okay, so what was the next step?
You balance everything except for oxygen.
Okay, so balance everything except for the oxygen, okay, or the hydrogens. So up here we have one Fe, one Fe. Is that balanced?
Yes.
Okay, down here we have 2 chromium and we have 1 chromium. Is that balanced?
Mm.
So for Cr, we have 2 on our reactant side and 1. Is that balanced?
No.
Okay, so if it isn't balanced, then what do we need to do to balance it?
The 2 on the
Put it on the where there's the one.
Add water. Is that what it said to do? To balance O atoms, add H.
First thing that we want to do is balance the other things other than the hydrogens and the oxygens, right?
Oh.
2 on your
So,
product side.
so we need to balance the chromium first, okay?
Okay.
So if we're balancing the chromium first, what do I need to do to balance the chromium?
2 on the product side.
So we need to put 2 on the product side. And we want to put 2 as a coefficient because we don't want to change what the chromium is. If we put it as a subscript, we change that chemical compound. And that is a different chemical compound. We never want to do that, right? Okay, so our chromiums are balanced. Now we need to balance the oxygens with water. So I have 7 oxygens here. So how many waters do I need to add to the other side?
7 waters.
I need to add 7 waters. Okay, so now I got 7 waters. So what do I need to add to the other side to balance out all of those hydrogens that I got now?
H pluses. It says
H
to add
pluses.
H pluses.
Okay. How many H pluses do I need to add, you said?
You now have 14 hydrogen from the 7 waters. So you would 14 on the left side.
Okay, so I have 14 H pluses added. Okay. So now that I got 14 H pluses, let's make sure that our equation is looking balanced. So we have 14 H on one side, 14 H on the other side. Chromium, we have 2 on the reactant side and 2 on the product side. And then oxygens.
You have. Would that still be 14?
Negative 14.
No, how many oxygens?
Oh, 7.
7.
And then on the product side?
7.
7.
Okay, so our elements are balanced. Now let's look at our charges. Okay, we have 14 plus. And then we have altogether, that's a 1, 2 minus.
Mm-hmm.
So what does that equal?
12.
Okay, on the other side,
You have 3.
we have 2,
Oh, 6.
6 plus. And then this is water. What is the charge on water?
Dr. Henry, the H is always going to be +1, right?
The H is always going to be +1. That's
Uh-huh.
correct. So what is
it?
the overall charge? Just we're talking about net ionic charge in this case. We're not worried about the
Oh,
oxidation number in this situation.
would you multiply the 7 like we did for the CR? How we multiplied the 2 coefficient with the 3+ charge?
So what is the charge on water?
On the charge on water, that's gonna be H is 1, oxygen is 2, there's 2 H's, so
It'd be 0.
0?
So you're multiplying 7 times 0, right? Because the overall charge on water is
0.
0, right? So if the overall charge on water is 0, it's going to be 0. So we have a big old 0 here. So we have a +12 and a +6. Are they equal?
No.
So 12 don't equal 6. So what can I do to balance out the charges on both sides?
It says to add electrons.
Okay, perfect. I need to add electrons. Which side am I going to be adding electrons to?
Your product.
Product.
Yeah.
Are you sure? Okay. How many?
No,
electrons am I gonna-
reaction. I mean, reactants.
My reactants. Okay. Because it also makes sense. It's being reduced, right? Which means you're gaining electrons. So we're adding electrons to this reaction, right?
Mm-hmm.
Okay. So how many electrons do I need to add to balance it out? So I have 12 here and I have 6 here. How many electrons should I add?
6 electrons.
Dr. Henry, this is 5, right? Step 5?
Yep. Okay, so we have 6 electrons added onto here. So we're looking pretty good now, right? Because that's -6. So then that just equals 12 minus 6 equals 6. And that makes it balanced on both sides. Okay, now let's look up here. We have Fe2+ and Fe3+. Are those balanced?
No.
No. So this is 2, this is 3. Okay, so how can I balance that?
Add an electron to your reactant.
To my reactant?
No, to
No.
your product.
To my product.
This is getting so confusing in the head.
Opposites, Maddie. Opposites attract.
Okay, so we add a single electron to that. So then we go -1. So then that equals 2, right? And if you look at it, Leo, loss of electrons. Oh, this guy is losing an electron. Okay, so that makes sense. Okay, so now here's the hard part, right? So I have 1 electron here, and I have 6 electrons here, and I need to balance these out so I can add the 2 equations together. So what do I need to do to that first equation?
The CR? The type?
First equation.
Oh, sorry.
I have 1 electron here, and I have 6 electrons here, and they have to balance each other out so the electrons are not visible in the reaction. What do I need to do to that first equation?
Put a coefficient, 6?
So I need to multiply it by a coefficient of 6. So I multiply the whole reaction by 6.
Dr. Henry, why are you doing the 6 from the bottom reaction on the top?
Because we have 6 electrons here, and we have 1 electrons here. Do they balance each other out? Does 6 E on my product side equal 1E on my electron side. Does 6 equal 1?
No.
No.
So you have to balance everything in the equation after you find out what's reduced and what's oxidated.
That's right. So the electrons have to be balanced. So what you have, the electrons that you're losing have to be equal to the electrons that you're gaining. Otherwise, the reaction won't happen.
Because this is going to become one big
Equation, correct?
Okay.
Okay, so let's go ahead and do that. We have 6, 6, and 6. Okay. Okay, so now we can add the equations together. So we have 6 Fe 2 plus 6E minus plus 14 H plus plus CR 2O7 minus and that's going to yield 6C. Oops, I got rid of my 3. Sorry about that. Six Fe 3 plus 6E minus plus 2 CR 3 plus plus 7 H2O. Okay. You guys get all that? Are your arms tired yet?
Dr. Henry?
Yep.
Would you not have to, or did you just not do it? The like ions and electrons wouldn't have one, but would the ions be the aqueous as well?
Yep. I just forgot. My bad. They're all aqueous. AQ. Oops. Good eye.
And your electrons wouldn't have one, right? They wouldn't have a state because they're just electrons.
Well, technically they're in solution as well, so they would have an AQ as well.
Okay.
But you'll see that they're going to cancel each other out, so it's not going to make a difference. Okay, so what are my spectators?
Electrons.
The 6 electrons. Does it matter which equations you write in the whole equation? Like,
What do you mean?
like you know how you put the reduction equation and the oxidation equation together?
Uh-huh.
Like how you wrote it out, you have the reduction first, and then you have the oxidation first, and then you have the reduction.
No, it doesn't matter.
Oh, okay.
Yeah. Okay, so then your final equation, I'll write up top. Okay. So do you want to confirm?
Did you forget the 2 on the CR?
Did I? Right here, my subscript 2. Thank you. Good eye. So let's do our quick confirmation. How many irons on each side?
6.
6.
How many H's on each side?
14.
How many chromiums on each side?
2.
How many oxygens on each side?
1.
7.
Oh wait, no, 7.
Okay, so 7 on each side. Okay, so we're balanced with the chemical equation. Now what about the charges? So what do we have here? We have 6 times 2 is what? 12 plus 14 minus 2. Then over here we have 6 times 3.
18.
Plus 6.
Plus 14.
You said 18 plus 14.
Yeah, you're 7H2O.
7H2O. What is the charge on H2O?
H2O was 0.
The 0.
Oh, my bad.
Okay, so I have 6 plus 18.
24.
So the total charge is plus 24 plus 24. Balanced?
Yeah.
That's it. Piece of cake?
So it doesn't matter that the irons have like different charges at the beginning as long as the charges like overall equal each other.
Yeah. And that's really what you're looking at because you're transferring electrons. The electrons are being transferred from one spot to another. So in this case, we're moving the electrons from iron to chromium on the other side of the equation. And so here we're literally transferring electrons. And so you have 2 different ions that are going to be existing. Are we good?
a lot.
Okay, good. Okay,
It's a lot. I need to remember.
Yeah, at least that was good. I just said it was a lot.
Yeah.
okay. Do you guys want to try one more?
Yeah.
Okay. Let's see, let me get to my whiteboard. Okay, so let me write the chemical equation up. Okay, and you guys know that this is hydrogen peroxide. Okay, so step one.
Break the into two reactions.
Okay,
Photo oxidize.
okay, who's Leo? Loss of electron, oxidation.
The MnO4. Wait.
Okay, so what is the oxidation number for Mn?
7.
7. So if we're going from a 7 to a +4,
You're gaining electrons.
I'm gaining electrons. Okay, so we already know our reduction. Okay, so by default, peroxide going to oxygen, that must be
Oxidation.
oxidation, right? Okay, So we broke it up into 2 halves. What is the next step?
Balance.
Balance. Okay, let's start off with the reduction one since it looks easier to me. So I have one Mn over here, and I have one Mn over here. Is that balanced?
Yeah.
Okay, we're good. We're good with that one. Okay, what about our oxygens? We got 2 oxygens here. I got 2 oxygens here. Are they balanced? Okay, so my oxygens are balanced. Okay, so we're good. Okay, so what is the next step?
The oxygens on the reduction reaction.
Okay, so the oxygens on the reductions, how do we account for those oxygens?
Adding
H2O molecules.
To which side?
Your product.
product
My product, how many am I gonna add?
4.
4.
So I'm adding 4. Okay, I got that. So
You have
that
to
means,
add 8 hydrogen ions to your reactant side.
okay, 8. Okay. So our H's balance out, our O's balance out. We're doing good. Okay, what about up here? Leo,
You have to balance out your hydrogen.
balance out my hydrogen. With what?
2 hydrogens on your product side.
Okay. 2 hydrogen, just 2 H's or 2 H?
Plus.
Would you still balance it with water? Or are you just doing,
Well, because we just need the hydrogens balanced now, right? Because aren't the oxygens balanced?
so you only add water to
Yeah, oxygen.
To balance
the
out your oxygen.
balance? Okay.
All right, my oxygen's balanced up here. I had
Yeah.
2 and 2.
Yes, so you would add 2 H ions.
Okay. Okay. So we got 2 hydrogens on both sides, 2 oxygens on both sides. Looking good. So what's next?
We have to
Dr. I
balance.
have a quick question before we move on. So we only add the water to, like, with your reduction reaction, how you're trying to balance the oxygen.
Mm-hmm.
So then because the oxidation has, we're just balancing the ions itself then at that point, right?
Yeah. Well, we don't have to worry about adding oxygen because we had the right amount on both sides. O2 here, O2 here. Aren't they the same?
Yeah.
Aren't they equal? So we don't need to add water in that case. So what do we need to add to balance out the hydrogens?
The hydrogen.
We're going to need the hydrogen ion. Okay. Okay, so then that gives me, so what was our next step we have to do?
Charges.
Balance out the charges. Okay, so how do I balance out the charges? So this one has a total charge of what?
You're frozen, so I can't, or well, my internet's bad, so you're frozen, so I can't see what you're pointing at.
What about now? Can you guys see anything?
There you go. No, my internet's just bad, so I think it's just me.
Okay. Okay, so on the reactant side, what is the charge on the hydrogen peroxide?
-2.
Hydrogen peroxide has a -2 charge on it?
It's
Yeah,
neutral, isn't it?
It's neutral. That is correct. Overall charge is 0, right?
Oh no, because there's no charge. Okay.
Okay. So what about here? What is the overall charge on this reaction on the product side? What is the charge on oxygen gas?
-2.
Oxygen gas is -2?
That'd be
Oh,
0.
wait.
0,
Zero.
right?
Never mind.
Okay. What is the charge on 2 H pluses?
2.
So it's 2. Is that balanced?
No.
So what do I need to do to balance it?
Add electrons.
To which side?
Product.
Mm-hmm.
How many am I going to add?
2.
2.
Okay, so that's 2 minus 2. That equals 0. So we have 0 equals 0. Good? Okay, what about at the bottom? The reduction reaction.
You have 8 for the hydrogens,
Okay. Oops.
and then -1, so -1. So it's 7.
8. And you said -1, so that's 7. Okay, and then what about over here?
Product, you have 4.
Okay,
And that's it, right? Because the H2 is 0.
that's right. H2O is 0. So 4 plus 0 is going to be 0.
4 plus 0 is 4.
4 plus, yes. Thank you, 4. Okay, so I have a +4 and I have a +7. Are they equal to each other?
No, you have to do 3 electrons on your reactant side.
Okay, so I need 3 electrons here. Okay, is that good?
Yep.
You don't need them to equal 0, you just need them to equal to each other.
No, they just have to be equal to each other. That's right.
Okay.
It doesn't have to be equal to 0.
Okay.
Okay, so what's next?
Combining them.
Okay, we have to combine them. Are you sure that's the next thing?
No.
We have to make sure like the charges are the same.
Okay, so what do you mean by that?
They have to like all add up to the same number.
Okay, what does?
The charges.
Is it the charges or the electrons?
The electrons.
Electrons. Okay, the electrons. Okay, So I have 2 electrons here and I have 3 electrons here. Is that going to add up?
No.
No.
So what do I need to do?
Would you have to multiply both now? Because it's 3 and 2, so you'd have to do like the top by 3, the bottom by 2.
Okay, so I multiply the top by, you said 3?
Yeah.
And then the bottom by,
You know.
two. Okay, let's go ahead and do that. So what is that? 3 H2 O2 aqueous plus, oops, not plus,
Yields.
yields O2.
Wouldn't it be 302?
Thank you. Plus, we have 6 H plus
6 E negative.
plus 6 E negative. And then our next equation would be what? 16 H pluses
Mhm.
plus 2 MnO minus, MnO4 minus, plus 6 E minus yields 2 Mn plus 8 H2Os
Now we combine them.
Yep. So now we can combine them.
Your manganese is aqueous again, right?
Yep. Thank you. And I forgot to put the charge on it. 4 plus. Okay, so we can add them together. Ooh. So that's what? 16 H plus plus 2 Mn O4 minus plus 6E plus 3H2O2 plus, oh, sorry, yield six H plus plus 3O2 plus 6E minus plus 2 Mn 2 plus,
That was 4.
sorry, thank you, plus 4 plus 8H2O. Okay, piece of cake. Now, what are my spectators?
Your electrons.
Electrons.
Okay. Anything else?
No.
Are you sure?
Wait.
Let me fix this.
You're Wait, no.
No, there isn't.
Mm-mm.
Okay. Actually, there is, but not in a traditional way that you guys are thinking about spectators. Hold on. Move this up a little bit. Maybe.
So are you going to break apart? Are you going to say that the peroxide on one side is a spectator because it equals the hydrogen and oxygen on the other?
Nope. Peroxide is not a spectator because that's one compound.
Oh,
But
okay.
we have the H plus, we have 16 here, and we have 6 here. All right, so in math, if I have an equation that has 16x equals 6x, what would I do in that situation?
NH plus. On the on the reactant side, you just okay.
So here, this guy will be changed to 10. So we lose 6 of these. So we have 10 H plus AQ plus our permanganate ion plus 3 hydrogen peroxides yields. So that guy's going to cancel. Even 10. 3 O2, 3 oxygen gas, plus 2 manganese 4 ion, plus water. Okay, the last step.
Wait, Dr. Henry. So basically, from what you're saying is that if we ever have an equation that, let's say, instead of the H, it was like an Br bromine, then we would have to do the same thing.
Yeah, so if this was Br plus over, I mean, Br minus over here and
Mhm.
Br minus over here, and there were 6 of them, and there were 7 of them, I mean, 7 over here,
Mhm.
we subtract. Yes, we just subtract. Long as they're exactly the same ion, right? Because these are both H plus, right?
Okay.
If they were different, like let's say we had Br gas and Br, then we don't do that.
Okay.
Okay. But only because they are exactly the same on both sides.
Oh, okay.
Okay. So what is the last step?
Check.
Just verification. Okay. So how many oxygens do I have on? Let's see. Do you mind if I erase some of the stuff up top so I can give myself room? Maybe. If it lets me. Okay, so here's our equation. Our final equation. So we need to verify, right? We have M, N, we have O, and we have H. Okay. On the reactant side, how many MNs?
2.
On the product side, how many MNs?
2.
On the reactant side, how many oxygens?
10.
So we have 8 plus 6. Is
14.
that correct?
Mm-hmm.
And that equals. And then on the products, I'm sorry, on the product side,
6 plus 8 is 14.
okay, hydrogens.
10 plus 6 is 16.
On the product side,
16.
okay, are we balanced?
Mm-hmm.
Okay, what about our charges? So we have 10 plus, and then what is this? What is the charge on this ion on the permanganate? What was that?
Minus 2.
Minus 2. And then on the peroxide?
0.
Okay, so then that equals
8.
And then over here, so we have oxygen, gas,
0.
and then we have the Manganese 4.
Plus 8.
And then we have water.
2.
Okay. So then that equals 8 and 8. We're all balanced. Happy? Want to go out and have a beer?
Please.
Shot of whiskey?
Tequila.
Know me too well.
Okay, so pretty long problem, right?
Yeah.
But pretty straightforward if you follow the steps, right?
Mm-hmm.
So the key is to remember the steps.
Yep.
Okay.
Dr. Henry?
Yep.
Our test corrections are due Wednesday and our homework is due today, correct?
Yes, but I may give you a little more time till the end of the week to get your homework done.
Okay.
Because it's chapter 14, I believe. I mean,
Okay.
chapter 4, not 14, sorry. Wrong class.
Yeah, I was going to say, I don't think we've gotten that far.
Okay, so let's see. I'm going to cut into some of our lab time. Sorry, they doing this. We got to get caught up. Let's do this. Can you see my screen?
Yeah.
Okay, good. Okay, so stoichiometry. Stoichiometry. Okay, how many of you guys bake cakes?
No.
Yes.
I have one person that bakes a cake. That's it. Out of 15.
Yes, I do.
I do too.
We all do.
I
Okay.
prefer
I'll
brown.
cook, I don't clean.
Okay, so you guys all bake cakes. Okay, so just for the record, I like strawberry cake with chocolate frosting with fresh strawberries cut on top, just so you know.
Okay, I'm not going to lie, Dr. Henry, that sounds horrible.
It is delicious.
Frosting on some strawberry cake.
Yes, chocolate frosting on strawberry cake. It's like strawberries dipped in chocolate.
It's not the same concept.
Oh, it is the same concept. It is delicious. Best cake ever. Best cake. Once you try it, you'll never try any other type of cake.
I like lemon cake.
I like lemon cake too, but strawberry cake with chocolate frosting and fresh strawberries. That's the cake. Okay, so tell me, how do you guys bake cakes? Let's see. I heard Mauricio say that he bakes a cake. So he's the only guy that spoke up. How do you bake a cake?
Well, it depends what type of cake.
What cake do you bake the most of? Do you make it from scratch or do you bake it from a box?
From scratch.
Okay, from scratch. Okay, that'll work. So give me your recipe. What is your favorite cake?
Oh, delicious, but I'm just gonna go simple with vanilla.
A vanilla cake? Okay, perfect. Okay, so vanilla
Yeah.
cakes. So tell me your ingredients on your vanilla cake.
Flour, eggs, then what else do I add? I think a little bit of butter, then the vanilla extract,
Okay,
and then
so let me make sure I get this right. I'm writing down the recipe here. So I'm gonna have flour, eggs.
excuse me.
I'm just asking you the recipe. You said vanilla, VANILLA.
Yeah.
You said butter. And what else? I'm assuming sugar has to go in there somewhere too, right?
Sugar for sure. Sugar for sure. Forgot to
Okay.
mention that one.
What else? What makes it rise?
Oh, I can't remember right now.
You're supposed to know this, right? You're
Baking
baking
powder or
this.
baking soda.
The yeast.
Okay, so we'll say, you said baking powder?
Yeah, baking powder or baking soda. Yeah, baking powder. Thank you, Tia. I'm having the brain fart right now.
Okay. If I remember correctly, there'll be some salt and some other things too. Okay, so that's a little complicated, right? Let's do simple. Somebody, how do you bake a box cake?
A box cake?
A box cake.
Oil, eggs.
You just add an egg, water, and then powder.
So you said box cake?
Yeah, box cake.
Eggs and oil.
You throw in the bag, you throw in some eggs, oil, and water, and then you cook
Oil, you said water,
And eggs.
Yeah, like
Okay.
two to three eggs.
Okay.
it. Mauricio said he forgot milk.
A lot of them don't ask for milk.
Okay. So
No, I
we
think for his.
for his cake. Okay.
No, milk.
Okay. So for a box cake, we use the box cake. We use oil. We're going to change that to butter because I like butter. I'm just letting you know what I like so you guys know, right?
Okay.
Okay. So how much oil am I supposed to add? How much butter?
I
I
think
like a
it's
lot of
like
butter.
3/4 a cup of oil.
3/4 of a cup of oil. So 3/4 of a cup of oil is about.
Maybe
let's
it's
see.
1/4. I can't remember. I just make brownies.
Okay, so if it's 1/4, if I remember correctly, that should be about a stick of butter. I think I'm exaggerating, but I'm going to say a stick of butter. Okay, so 1 stick of butter. How much water?
Usually around a cup.
Okay, about a cup. So 1 cup. And how many eggs you said?
Like 2 or 3.
Yeah, 3.
Okay, 3 eggs. Okay, and that's going to give me my cake. Okay, so I have 1 box cake, 1 stick of butter, 1 cup of water, 3 eggs, and that's going to give it a cake. Is that correct?
Yeah.
Okay, good. Okay, so let's say this is 1 whole cake. So, and we'll say 1 whole cake is about how many pieces of cake per person?
Depends
Now,
on
this,
how
we're
many,
talking about
or how
adult.
big you cut it.
What was that?
Depends on how big you cut it.
So we're cutting adult sizes. So what is
Well,
that, 6
Daddy's like
pieces?
a whole row by himself, so
We'll say 6 pieces.
6. Oh my god.
Yeah, 6 pieces. So 1 cake is about 6 pieces. Okay, so we have 15 people in this class. How many cakes do we need to make?
15.
You said it serves 6 people. And we have how many people in the class?
We have 15 people in the class. Well, I'll count as see, make it even. I'll count as 3 people or 4 people. So we have 18 people in the class now. So we have 18 people in the class.
3 cakes.
Okay. So it's 1 piece per person, right? So that's a piece of cake. So we need 18 pieces of cake. You said 3 pieces 3 cakes?
Mm-hmm.
Okay. You guys can't read my handwriting, can you? So I have 18 divided by 6 pieces of cake, right? Equals for 1 cake. Okay, so then how many box cakes am I going to need?
I thought we were talking about box cakes.
We were just talking about the cakes.
It's a box cake still feeding 18 people?
Yep.
Or I mean 6 people. Or 6 pieces, I mean, in each cake.
So for every 1 cake, there's 1 box cake. Or cake box, or whatever you want to call it. Okay, so then that's going to equal, you said 3 boxes. How many eggs am I going to need?
9.
Okay, so again, I can use that ratio that you just told me. So we had 18 pieces. Six pieces per cake. One cake. And we know per cake we need how many eggs? You said?
Per cake is 3.
How much water?
For 1 box or for all 3?
For all 3?
3 cups.
3 cups. How many sticks of butter?
3 sticks of butter.
Okay, so you're telling me that I can sit there and use ratios to sit there and figure this all out. Is that what you're telling me?
Yeah. Or double or triple the box.
Okay, so if I wanted to make, let's say, 2 pieces of cake, just 2 pieces, do I have to use my whole box?
Nope.
So I could actually calculate how much it would take just to make 2 pieces of cake, right?
Yep.
So you mean I can scale up and scale down?
That's
using,
what we're saying.
Is that true, really?
Yep.
Okay, so that is just basically stoichiometry. Stoichiometry is using the ratios that we have for like a recipe to sit there and to be able to scale up and to scale down. Okay, so it's just using the quantity of what we're using. How many box cakes are we using, right, for 1 cake?
1 box.
So 1 box per cake, right? How many sticks of butter are we using?
1.
It's a 1-to-1 ratio, right? How many cups of water are we using per cake?
1.
How many eggs?
For
Per
1
cake.
box is 3.
Okay, so a 3-to-1 ratio, right? So, do you guys get that?
Yeah.
Piece of cake?
That was
Okay.
a bad pun.
Okay, I thought so. Okay, so it's real simple, right? So we can use these relationships, right? These are the same relationships that we're going to be using in chemistry. And so it's just setting up those chemical equations that we're going to be doing different, right? So it's not that hard. And you notice we have coefficients in here, right? And so that is going to be the distinction. So we're going to use those coefficients to help us set up our chemical equation. We know for 1 box cake, we had 1 stick of butter. We had 1 cup of water. We had 3 eggs, right? So those coefficients tells us how much of the compounds that we are going to be looking at. So you want to try to apply this to chemistry real quick? Okay, so the very first thing that we always want to do is balance a chemical equation. Not too far. Okay, so is our equation balanced?
No. Wait, yes.
Everybody agree? Is it unanimous?
Unanimous.
Yes, it's balanced.
Yeah.
Okay,
Yeah, it is.
good, good, good. Okay, so we have a balanced equation. Okay, so if I'm looking at my equation right now, and I have one nitrogen molecule, how many hydrogen molecules will I need to react completely with that one nitrogen molecule?
3.
3, okay? So then I could say, for every one molecule of nitrogen, I'm going to need 3 molecules of hydrogen. Is that cool? Okay, so now I'm going to ask you another question. So if I have 1 dozen molecules of nitrogen, how many dozen molecules of hydrogen will I need to react with it?
Like you put a 6 coefficient in front of the N2 to make 12?
Okay, so let me ask you again. If I have 1 dozen of nitrogen molecules, how many dozen of hydrogen molecules will I need to react with it?
3.
3.
Dr. Henry, can you hear the noise coming from my house? Should I put myself on mute or is it
I
okay?
can hear it, but it's no big deal.
Okay,
It
my
just
mom.
sounds like you have
Cabinets.
it just sounds like you have gas, that's all.
No, my mom's getting the cabinets painted, so they're using the spray gun.
Okay.
I'm gonna mute myself.
Okay, so if I have 1 mole of nitrogen, how many moles of hydrogen will I need to react with it?
3.
Okay, so the moral of the story is, right? Whether I'm talking about 1 molecule or I'm talking about 1 mole of molecules, the ratio is always going to be the same. Okay, so if we have a balanced equation, then we can calculate how much we can actually generate based upon that ratio. Okay, piece of cake?
Yep.
Okay, and that's the same thing that can be said for the amount of ammonia that is produced. So if I know how much hydrogen I have, and let's say, and the amount of nitrogen, I can calculate how much ammonia I will be producing. Right? Okay. Questions, concerns, cash, credit. Cake. Okay, so How many molecules of I2 are required to react with 0.429 moles of aluminum, according to the following equation? A2 plus 3 iodine gas yields aluminum iodide. 2 aluminum iodide. So what am I going to do? What is my given?
0.429 moles of aluminum.
Okay, so we have 0.429 moles of aluminum. Guess I should put the units there. So, and I want to calculate, what is my goal? What do I want?
You want moles of I2.
So I want moles of I2. So what am I going to do?
Use your molar ratio.
I'm going to use my molar ratio. Okay, so what is my molar ratio?
2 to 3.
2 to 3. So
2
what about
AL on the bottom.
So 2 moles of Al at the bottom.
And 3 moles of I2 on the top.
3 moles of I2 at the top. Okay, so then that'll cancel out, and then I'll just be left with moles of I2. How many sig figs should I have?
3.
3 sig figs. Okay, questions, concerns, cash? Credit. Piece of cake?
Yep.
Okay, so let's make it a little challenging. Okay, so if we're giving mass, right? Again, the first thing that we're going to want to do is to balance our chemical equation, right? Our chemical equation has to be balanced. Now, again, we want to make sure that our coefficients just tells us how many of that particular chemical we have. So we need to make sure our chemical is the correct chemical that we're looking at. If that is the wrong chemical, that is going to be a huge problem, right? And we don't use our coefficients to balance our chemical. Our chemical is what it's supposed to be, right? So in this case, this is a piece of cake because it's already balanced for you, or is it?
It's balanced.
Okay, so this guy's balanced for us, right? So since it's balanced for us, it says what mass of sodium hydroxide, NaOH, would be required to produce 16 grams of antacid milk of magnesium hydroxide, MgOH2, by the following reaction. Okay, so what's my given?
16 grams
16 grams.
of milk of mag.
Okay, so I have 16 grams of MgOH2. Okay, so I have a question. So these are grams. And our balanced chemical equation, is that going to be based on mass? Or is that going to be based on quantity?
Quantity, isn't it?
Quantity. What is the difference?
We want mass. Quantity is how much, mass is like weight.
Okay, mass is weight, right? So for instance, if I had 2 apples, right? And I'm making, what is the Jello called with the fruit in it? Fruit Jello? I don't know what it's called. Okay, we'll say ambrosia. Do you guys know what ambrosia is?
That's what I was thinking that you were talking about, but that's
Okay. Okay, we're gonna say ambrosia. Okay, so but in my ambrosia, I'm gonna put apples and grapes. Okay, so the recipe calls for 2 apples and 20 grapes and whipped cream. So am I gonna weigh my apples and then put in the same amount of weight for my grapes?
Because you just put in your quantity, how much.
Okay, so I'm not going to sit there and weigh 2 pounds of apples and put in, 20 pounds of grapes to match it, right? Because we're talking about quantity. We're not talking about mass. Do you guys get that? Do you see the distinction?
Mm-hmm.
Okay, so first thing that we want to do is anytime that you're given grams, you want to change to moles. And how do I change it to moles?
Molar mass.
Molar mass. So what is the molar mass of magnesium hydroxide?
$58.
Okay. And how did you get that, Matt?
By adding the molar mass of the compound.
Okay. Good job. So, going to put the grams on the bottom and the moles on top. Okay, and what do we want? What is our goal ultimately?
Mass of sodium.
Mass of sodium. So we want grams of sodium. So we're going to use moles as like our gateway drug, right? So we're going to go from moles, from mass to moles. Then we can do a ratio. What is the ratio of sodium to magnesium hydroxide? Here's magnesium hydroxide. Here's sodium hydroxide.
2-to-1.
It's 2-to-1 ratio, right? So then we'll use that to our advantage. So we know that we have 1 mole of magnesium hydroxide on the bottom here. And we have 2 moles of sodium hydroxide. Oops, getting anxious there.
So now you do your molar mass.
Then I use my molar mass. So what is the molar mass of, at this point we're looking at what compound?
your sodium hydroxide.
My sodium hydroxide. Okay, so what is the molar mass of my sodium hydroxide?
63.
You said
63.
53? 43?
63. 63.
Are you sure? 18 plus 23?
18.
I mean, not 18. Yeah, 18. I mean, sorry. It should be 6, 15,
There's
15, 17, 17. Sorry.
40. I put too many oxygens.
Okay, 40 grams. Okay. So we are left with how many sig figs?
2.
2. Is that correct? That should be an H here. Piece of cake?
Yeah.
Okay. Okay. So ultimately, knowing what you guys know now, you guys know density. Is that correct?
Mm-hmm.
So if you're given the volume of a pure substance, then we can use its density to determine the mass, right? Because we know that density equals volume, mass divided by volume. So if we have the mass of a substance, then we can use the molar mass to get the number of moles. If I have the molarity, right, then I can use the volume to get the number of moles. And then I can use my stoichiometric ratio to find how many moles I'm going to be producing of the other one. Okay, so now I can calculate the number of moles of B. From that, I can calculate the mass. I can also calculate the volume. Right? Or I can come over here, use the molarity, and calculate the volume of the solution. Or I can even calculate the number of moles. I can calculate the number of particles of B we have using Avogadro's number. Okay, so you should be able to do all of these things at this point. Questions? Concerns? Cash? Credit? Good, perfect. Let's move on. Okay, so we're going to be talking about reaction yields. Now, when we talk about reaction yields, one of the things I want to kind of concentrate on is limiting reagents, right? So, how many of you guys like cheese sandwiches? Abby, you like cheese sandwiches?
Yeah.
Just cheese? You need something else in there.
Grilled cheese sandwiches with
Yeah,
all the
like
butter
that.
and everything.
Okay.
Grilled cheese.
Yeah.
I think that's what I'm going to have for lunch. Grilled cheese sandwich. What about you, Amanda? Do you like grilled cheese sandwiches?
Yes, I love grilled cheese sandwiches.
Love them. With tomato soup. Oh my gosh.
Oh,
just
yes.
Dip it in. Oh, delicious, right? Okay, so recipe for a grilled cheese sandwich is, let's say we have big hunks of cheese and 2 slices of bread, right? And then we, of course, you're going to put the butter and everything on it, but basic is cheese and bread, right? So 1 piece of cheese, 2 slices of bread. That's going to equal 1 sandwich. Okay, now I want you to think about this. Now think hard. Okay, so if I have 11 slices of cheeses and I have 28 slices of bread, how many sandwiches can I make? Will I have enough to make one for the whole class? There's 15 of us here.
No.
No. How many cheese sandwiches will I be able to make?
11?
22.
11. And how did you figure that out?
Because you got 11 cheese and you're using 2 breads for each. So 2 divided by 2. I mean, 11 divided by 2.
Perfect. So what's in excess? What do we have extra of? And what do we have not enough of?
Limiting cheese and excess bread.
Okay. So we're limited by cheese, right? So because we're only able to make it, I should have added a couple of more slices of bread to make it so we could have enough people. But we're limited by the number of cheeses that we have. And so in this case, our bread is going to be in excess. So the cheese would be our limiting reactant or our limiting reagent. And then the bread would be what's in excess, our excess reagent. Okay, so you're always going to be limited by the one that you have the least amount of, right? Now, you got to be careful about how you look at it, right? Because again, we're talking about quantity, not mass. And not everything weighs exactly the same. Do an apple weigh the same amount as a grape? Let's see. Tia, does an apple weigh the same amount as a grape?
No.
Okay, so we want to make sure that we're looking at quantity and not mass when we look at this, right?
Yes.
Okay, so that's going to be essential. Okay, so when we're working with limiting reagents, we always want to sit there and determine which one is going to be the least of our products. Okay, so let's assume in this situation that we have 3 moles of hydrogen gas and 2 moles of chlorine gas. Which one is going to be limiting?
Chlorine?
Okay, so why is the chlorine limiting?
Because there's less of it?
Because there's less of it. And if we look at the molar ratio between hydrogen gas and chlorine gas, what is the ratio?
3 to 2?
The ratio in the chemical equation.
Oh. 2 to 2?
2 to 2, okay. Or 1 to 1, right?
Yeah, okay, sorry.
1 to 1. So it's a 1 to 1 ratio, right? So for every 1 hydrogen gas I have, I'm going to need 1 chlorine gas. So we know that we'd run out of chlorine before we'd run out of hydrogen. Simple?
Yes.
Okay, so again, we want to be looking at the ratios, and we want to compare the ratios to each other. So mathematically, to show it, I mean, other than looking at it, we can clearly see, right? We want to show that mathematically, right? So if we had 3 moles of hydrogen gas, we're going to need, for every 1 mole of hydrogen gas, we're going to need 1 mole of chlorine gas. So then, if we had 3 moles of hydrogen gas, we would need 3 moles of chlorine gas to react with it. And how many do we actually have? How many do we actually have?
2.
2. Okay, so that clearly tells us that chlorine is going to be our limiting reactant, where the hydrogen is going to be the one in excess. Piece of cake? Not too hard? Yeah, no, maybe?
Yes.
Okay. And the beauty of this is that we could have gone about it several different ways. We could figure out which one is going to give us the most of our product, right? And then that way we'd have to do both equations. Or we can do a comparison with each other. And if you're doing a comparison with each other, you always want to compare apples to apples, right? You don't want to compare apples to oranges because that could lead us down the wrong path, right? So what I mean is that if we go back here, by us looking at chlorine, we're comparing the amount of chlorine that we would need if we started off with hydrogen gas to what we actually have of chlorine, right? We're not comparing that to hydrogen. Do you understand? So we want to compare what we would need to what we actually have of that same gas. Okay, or you could sit there and calculate both equations and just figure out which one gives you the least amount of yield. But in one case, all you'd have to do is do it for one of them, rather than having to do 2 sets of independent equations, right? But this one will give you the correct answer all the time. It's just more work. Any questions? Okay, great. No questions means that I can give it to you on the test right now, right? Okay, perfect. Moving on. Theoretical versus actual. So theoretical is the calculations you're getting from your chemical equation. Your actual yield is what you get when from the actual experiment that is done, right? So for instance, I took a course in analytical chemistry and when I was an undergrad. And we would do labs and everything like that. And, you know, I was sitting there, you know, I'm a smart ass. I'm thinking, I know my shit and everything like that. So I started the experiment and I do my experiment. And then we had an instrument that would determine whether or not our yield was accurate. Of course, we had scales or some type of instrument to sit there and to make sure that we had our yields. We could calculate the yields based upon that. So I did my calculations, and then you always compare your actual divided by your theoretical, and you multiply it by 100. And that's going to give you your percent yield, right? So percent yield equals actual over theoretical. Now, if you had done your experiment right, you should always end up with, let's say, if you're perfect, there are no issues with the experiment or anything like that, you should get 100%, right? 100% yield in theory. There's no issues with that experiment. There's no lag or anything like that, 100% in theory. That's the best you're going to get, right? 100%. Like on a test. What is the best you can get on a test?
100%.
100%. Good. Okay, good. So since you can only get 100%, we know if you got 200%, there's an issue, right?
Yeah.
And if you got 80%, you didn't get something right. You screwed up somewhere, right? In theory.
Yeah.
Okay. So that's my thinking as well, too. Particularly since, these are the first times I actually did real labs, because I did go to high school in the Valley. And if we did a lab, it was probably one every blue moon. And so we never did anything where we calculated percent yield or did true calculations, right? So I'm going through an idea of my experiment. And the first time I do it, I get 82%. I'm like, okay, shit, did something wrong. Let me do it again, right? And I was pretty quick, let me go at it again. Get it done. 82%. Do it a third time. 86%. Okay, so I got 86%, 82%, 82%. Now, my first thought is I'm doing something wrong, right?
Yeah.
So I made a mistake. Let me go back. And, I'm quick at doing these experiments. So I'm like, okay, I may be able to squeeze one more in here before, class is over and everything like that. So let me try one more time, but let me check because obviously I'm doing something wrong, right? Maybe I missed one of the steps. So I go back to the original lab, open up the book and I read it. And I'm like, yeah, those are the steps I have in my lab notebook. These are the steps that I followed. I did everything I was supposed to do, right? And then so, I'm talking to my friend next to me right here, like, hey, what did you get for your yield, right? And he's like, well, I got 100%. And okay, right? So then clearly I'm doing something wrong. So go and I do it one more time, right? I'm like, fuck, okay. So then still I get 82%. Okay, so 3 times 82%, 1 time 86%. Right? So accurate or precise? Precise, right? So I'm pretty damn precise, but I'm not accurate because I'm expecting to try to get 100% yield. I should be getting 100% yield. If everything was fine, I should be getting 100% yield, right? So what do you think I did, right? I'll tell you what I did. So I'm a little pissed off, right? I'm like, okay, I talked to the TA. The TA has another section in the evening. So I'm like, hey, can I come to your section in the evening because I didn't get the lab done because I screwed up, right? And he's like, okay, that's fine. He's like, you come in. He says, usually there's a spot or something like that. You can do it again. I'm like, okay, that sounds great. So I go back in the evening. I do the same experiment. I get the same type of numbers, right? 82%, 82%, 82%, right? And I am pissed, right? I had a temper at that point. I know it's hard to imagine because I'm so calm, cool, collective. I never yell or anything like that to you guys, so it's hard to imagine that I would have a temper, but I had a temper, right? I was livid. I threw my lab notebook across the room into the garbage can, right? God damn it, I'm cussing the whole way out. And I'm like, I am done, right? I'm pissed, right? Because I had done it over and over and over again. And I kept getting the same number. So obviously, this is not what I was meant to do, right? That's what my thoughts were. I am like, I'm an idiot. I can't get this damn experiment to work. I'm only getting 82%. I am not getting that 100%. I want that 100%. I must be screwing up. I must not get it. I must be doing something wrong. And I'm in the wrong field. I'm quitting, right? So I'm cussing and going out the thing and I'm kicking the trash can and everything like that. And I start walking out and everything like that. And I get halfway, a little way from the door and everything. And then the TA comes out, Mr. Henry, what the hell's going on? I'm like, I suck. I said, I'm not meant to do this. I'm just gonna fuck it. I'm done. You know, it's just like, I can't handle it. This is just, you know, I had a moment. I was cracking, you know? I was like, I'm a fucking idiot. I can't get this to work. Everybody else got 100%. I'm not getting 100%. I'm screwing something up. If they're able to do it and I can't compete with them, why in the hell am I misfit? I need to change my major. I need to figure something else out, or I need to just quit college altogether. You know? That's it. I'm done. Right? And he's like, what percentage did you get? Right? And I told him, I said, I got 82%. He's like, Mr. Henry, come here. Come here. Come with me. Right? So we go into the back of the lab and everything where all the chemicals were stored. And he pulls down the bottle that we're using. He's like, so this is what your solutions were made with, right? Look on that bottle. And then I looked on the bottle and it says molecular grade, right? Molecular grade was anywhere from 81 to 86%. So depending on that particular one. So it had a range of the percentage that it was. So that meant that there were impurities, right? So often when we're thinking about yield, part of that could be a result of impurities, right? Being kind of new to chemistry, being the first time that I've been in the lab, I didn't think about impurities, right? Do you guys think about impurities when you're thinking about something? You think about it being pure, right? Most chemicals on the shelf that you're getting, most drugs that you're getting, do you think about them being pure? Maddie, do you think about them being pure?
Dr. Henry, my thing's glitching again, so I hear you, but it's like, I don't know if you can hear me, but that's how I heard you.
Okay. So Darlene, what about you? Do you think about them being pure? The medications you get.
Yes.
Yeah. So we make the assumption that the things that we're getting are pure, right? But in actuality, a lot of them have impurities, right? So the probability of you getting 100% yield is probably not going to happen, right? And of course, it could be something like what we did. I was thinking it was me, right? But in actuality, it was just the starting material that we started out with was 80 to 86% pure, right? So I almost threw away my whole career had my TA not talked to me and talked me off the ledge. I'd have dropped out of school probably, or not even finished my degree, right? As a result of purity, right? So I always like to tell this story because percent yield plays a huge part in my life, right? And so when we think about it, percent yield is always going to be the actual over the theoretical. And in theory, you should always end up with a percent yield lower than 100%, you know, because reality checks in. You're never going to get the perfect reaction. As much as we try, there's always going to be something a little bit wrong with it. Usually the materials that we're starting out with are not as good as we think they are. And so we have to take that in consideration. When we're doing a drug administration, right? So how long the drug has been on the shelves. So a lot of time the dosage is dictated by shelf life, right? So there's a decay in certain drugs, a result of them being on the shelf longer. And so the pharmacist will take that into consideration, right? So when administering, the activity of a particular drug is basically your percent yield. How much of it is actually going to be effectively given to this patient the way that you're administering? That's taken in consideration. Okay, so percent yield plays a huge part in what we do. We call it different terms in different fields, but it boils down to how effective that drug is overall. Okay. Are you with me?
Yes.
Anybody want to jump off bridges yet?
closer.
Not yet.
Not yet. Good, good. We want to keep it like that, okay? So don't throw in the towel because you're not getting that perfect yield, okay?
Can you hear me?
I can hear you now.
Okay.
Okay, so come on. And then we'll stop here because I think your brains are probably fried at this point. Right? Okay, so the question is, upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.92 grams of copper metal was obtained according to the equation. What is the percent yield?
So you do the 0.392 divided by 1.274 times 100.
Are you sure?
Well,
Because this is
actual
copper metal and this is copper sulfate.
Oh, dang it. Oh, you have to do your multiple.
Okay, so my
The
given
term.
would be
So you
or the given that I should be starting off with.
we went from copper sulfate to copper metal.
Okay, so we need to go from copper sulfate to copper metal. So
Yeah.
we want to go
1.274.
what is the chemical formula for copper sulfate? And it's copper 2 sulfate. I forgot.
Sulfate, so it's just CuSO4.
Okay. And then what am I going to do with that?
The molar mass, because you want to go to moles.
Okay, so the molar mass of copper sulfate is
159.62 grams.
okay. So then we have moles of copper sulfate, copper 2 sulfate. So what do I need to do to get the theoretical amount of copper?
Apples to apples, right? So 1 mole of CuSO4 to 1 mole of copper.
And then if we want the mass,
So you go 1 mole of copper on the bottom, and then you do your grams. So 64 grams of copper on top.
copper only weighs 4.
4.
Are you sure?
No,
Copper,
you do what you were given. So the 0.392 grams.
but okay, we have moles of copper here, right? So don't we need mass of copper to compare the mass? Because we're given, this is the mass that we're given, right? So we want percent yield. Percent yield is usually theoretical over actual. Actual over theoretical, right? And so we're talking about this is our actual. So how do I calculate my theoretical mass? So I have 1 mole of copper.
Yep.
How do I calculate the mass of that copper? So that means
So you wouldn't use your mass, or you are?
would I use my mass? Because
Or
we're
do you
talking about
use,
1 mole of copper. What are we going to use for that?
the molar mass, right?
Molar mass. Okay, so what is the molar mass of copper?
That's what I said earlier, and you said no.
No, you said 4.
I said 64.
Oh, you said 64. My bad.
That's okay, because I was really confused. Like, well, if it's not the actual, then it would be that one.
All I heard was 4. And I'm like, the molar mass?
Oh.
Yeah, okay.
I said 64 because I rounded.
My bad. My bad. Okay.
Okay, Andrew, don't do that to me. I'm on a roll right now.
Sorry about that. I heard 4. That's all I heard. So I was like, what are you calculating? Right? But I didn't say it like that. I was calm, cool, collected.
No, but you wanted to say something else to throw something at me.
Exactly. Okay. So what do you guys get?
51.
How many sig figs should I have?
3.
How many? I heard
4, right?
4. That's right.
Oh, oops.
51.08 then.
Okay. Okay, so now we got the mass, the theoretical mass, and this was the actual mass. So what do I use to calculate percent yield? Percent yield equals
Actual over theoretical.
actual over theoretical. Times 100. How many sig figs should I have?
4.
So I have 3 up here. So 360, wait, 392.
Oh, 3.
Yep.
3 sig figs.
Okay. So I got 76.7%. What did you get?
I got that same thing.
Okay, piece of cake.
Yep.
Good, 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 good. Okay. Okay. Okay, so we'll stop there and then we'll finish up the last part of the chapter and start chapter 5 on Wednesday. 10 slides left. Questions, concerns?
Nope.
You said you were going to extend the homework a little more?
Yep.
Okay. Okie dokie, that was my only question.
Okay, yeah, and at this point, you should be able to do everything on the homework.
Okay.
The only thing that's left, I mean, you guys already know how to do empirical equations because you guys did that the last sections. So the last part is just going through.
So when you're calculating percent yield,
Mhm.
does it matter if it's in grams or moles?
It doesn't matter if it's in grams or moles if you're consistent, because you're dividing both of them by, like if it is in grams, you're dividing it by the molar mass. And if you have the molar mass of one of that chemical divided by the molar mass of that same chemical, it should be exactly the same.
Right.
So
Okay.
So yeah, you could get away, if you're given, you can do it in moles or you can do it in mass, but you want to be consistent that you're using either moles or mass, not both of them.
Yeah, right. Thanks.
No problem. Good thinking though.
Okay, I have a kind of goofy question for you.
Right, I have a kind of goofy answer for you.
How do you get concentration again?
Concentration, well, concentration depends on what we're talking about. So we could do molarity, right? Which is moles over liters, moles of solute over liters of solution. We could do percent mass, which is mass of solute over mass of solution. Or we could do mass volume, right? Which is mass over volume of solution, right? So all of those are examples of concentration. And long as you're consistent about it, you can use that to sit there and calculate your dilution.
Okay.
Okay. Does that help?
Yes. And then there was one other question I had about the homework because I got really confused on it. It's the how to set up the table of the reactants.
The ICE tables,
Yeah.
I may be dropping those problems, but ICE tables just stand for, ICE stands for your initial concentration, your change, and then it's usually E stands for equilibrium or endpoint, right? So initial concentration is what you're starting out with, the concentration you're starting out with. Your change depends on what you're talking about at that particular time. How is it changing? And then, so usually you're subtracting a change that's happening. And then your endpoint would be the concentration that you end up.
Okay.
Okay.
Okay, I think that checks off my questions.
Dr. Henry, what's an osmol? Jessica said no. You gotta ask you.
Okay, so osmol is osmolarity. It deals with osmolarity. You guys weren't supposed to be going over that yet. So you guys have a question that deals with osmolarity?
Yeah.
Okay, so osmolarity deals with it deals with osmolarity. It deals with the pressure across a membrane, essentially. And so it deals with that gradient that exists in like cells and stuff like that. So what I'll do is,
because it's number 90 on the homework. This is how many osmoles are in 1 mole of Na2.
okay, so I'll take that one off for you guys so you guys don't have to worry about it.
Okay.
Yeah, because we will be talking about it, but not yet. So, and I didn't want to go over it yet. So number 90, right?
90.
And then the ICE tables are which ones?
16, 17, and 18.
16, 17, and 18. Okay.
That's horrible because I think Matt, we have 1 left. It took us like hours to do.
I know, it took us literally like an hour just to do like 1.5.
Yeah, they're a pain in the butt.
Yeah.
And it seems like so much extra work for what you're getting out of it. You know, you're like, really? But they're going to be important because you're going to use ICE tables later on when you start talking about equilibrium. And they're really important for equilibrium stuff. So you can't escape them.
But not now.
but not now. Yeah,
But
you don't
they're
need them for
here.
now. Yeah, for the questions that
Yeah.
you're asking, they shouldn't have used that. Yeah. So I'll make that adjustment. Any other questions? Okay. Okay, then I'll say peace and I'll see you later.